In this example, we are going to try to graph this as accurate as we can, which means we are going to graph all its pieces as highs and lows and inflection points by using first derivatives and second derivatives. So before we dive into that, I'm going to take kind of a pre-calc college algebra look at it. We have something that's an x to the third, and so we have no domain issues that we need to worry about. So our domain is going to be everything. And then end behavior, I have a positive x to the third. So I know that this is going to be heading in this direction and this direction. And then we can do our x-intercepts, which we're going to have to do a little bit of math on that. So before we do that, let's do our y-intercept. So if we do a y-intercept, we would be plugging in 0 and we would get out 0. And so for our x-intercept, we would be taking this equation and setting it equal to 0. And so we're going to take x cubed over 3 minus 400x, set it equal to 0, and figure out how to solve that. So we'll start by taking a factor and an x out. And then that would leave us with x squared over 3 minus 400 equal to 0. We'd set each factor equal to 0. X squared over 3 minus 400 equal to 0. And so there's one x-intercept, which is also a y-intercept. And so we have that. And then if we add 400 and then multiply by 3 over, we're looking at x squared equaling 1200. And then we would square root both sides. And since I'm trying to graph it, I'm going to get the decimal version of this. So if I were to plug that into a calculator, I would get a plus and minus. Square root of 1200 is about 34.6-ish, right? So those three are our x-intercepts right there. So we have that. So there's kind of the college algebra pre-calc-ish part of this. I know that we have some sort of an end behavior. So kind of where we sit is we have these three x-intercepts. And since it's positive with our end behavior, we're looking at that. So that's where we sit. But we're going to get a little bit more detail. The idea is for calc, we're going to figure out where's the high point, where's the low point, and when do we shift this concavity from concave down to concave up. And that's where the first derivative and second derivative stuff's going to kick in. So first derivative. So if we take this derivative, here's kind of why the 1/3 is sitting in front of it, is I would look at this equation more like this to do the derivative. Because when I do my derivative, it's going to nicely cancel out. May not need to do that, but x squared minus 400. Then if we set this equal to 0, x squared minus 400 equal to 0, we'll add 400, so x squared equals 400, square root, and then x is going to equal plus or minus 20. All right, so we get maxes and mins at 20. Most likely the negative 20, so positive 20, negative 20. Most likely the negative 20 is going to have to be a maximum and the positive 20 is going to be a minimum. Let's actually plug them in and see what we get. So if we plug in negative 20 and we plug in positive 20, we throw that into a calculator, we would get the negative 20 gives us 5,333. And then the positive 20 gets us a negative 5,333. All right, so those are our critical points. Again, just based on what we would have known already, we have our maxes and mins, but we're going to take it a step further in a second and take those critical numbers and really kind of verify that all of this looks exactly like we think it's going to look. We'll come back to that. So next thing is we need our critical numbers from our second derivative, which the derivative of that is 2x set it equal to 0. Our critical number is 0. All right, so, and we already know that if you plug in 0, you get 0. So here's our last piece of this is we're going to do a number line. We have first derivative, we have critical numbers at -20, +20, and second derivative, we have a critical number at 0. We're going to test our slopes on each side of this stuff to make sure that it's all lining up with this and get a really accurate graph. So if we were to plug in anything to the left of -20 into our first derivative, and we take like a -30 and square it, we're going to get 900 minus 400 is going to be positive. We take something in here like a 0, square it and subtract 400, we're going to get a negative. And then taking a -30 is no different than a +30 because you're squaring, you're going to get a positive. So we're going to have a positive slope transitioning to a negative slope transitioning to a positive slope. So there's our max at the -20. There's our min. There's our justification of how this works, other than here's what we think is happening. And then concavity, we should have concave down and concave up here. Let's see if that agrees. And then we kind of guessed that would happen as well. So if we take a -1 and plug it into the second derivative, we're going to get a negative value, implying a concave down. And then we plug in a positive, we get a positive, which means concave up, which those very much line up and agree with each other. And now we have everything we need. So our graph, as accurate as we could do, would be, we would have 10, 20, 30, 40, 10, 20, 30, 40. So -40, -20, 20, 40. And we would have x-intercepts at about 35-ish. -35, +35, and at 0, we would have a maximum at -20. And this value would be 5,333. We'd have a minimum at -5,333. And that would happen around here. And so we would have positive slopes till we get to that maximum. Then we have negative slopes. And we have an inflection point as well at 0. So that inflection point is our concavity is shifting from concave down to concave up. All right, so we were totally heading in the right direction with all of this, but we needed justifications for all of this. And so how do we know that that's happening? How do we know that that's happening? Our best guess, we were pretty good, but we needed more detail. Like, where is that maximum? Where is that minimum? And that's the first derivative. And then the second derivative is validating all of our concavities and things like that. So that's putting all the pieces together to try a graph and make it as accurate as we can.